Out there in space, blazing just a scant 150 million kilometers away, lies the brightest and most massive object in our solar system known as the Sun. Shining hundreds of thousands of times as bright in Earth's skies as the next brightest object, the full moon, the Sun is unique among solar system objects for producing its own visible light, rather than only appearing illuminated because of reflected light. However, the thousands upon thousands of stars visible in the night sky are all also self-luminous, distinguishing themselves from the planets and other solar system objects in that regard. Unlike the planets, Sun and Moon, the stars appear to remain fixed in their position over time, not only from night to night, but also throughout the year and even from year to year. Compared to the objects in our own solar system, the stars must be incredibly far away. Furthermore, in order to be seen from such a great distance, they must be incredibly bright. It only makes sense to assume, as many did dating back to antiquity, that those stars must be sun-like objects located at great distances from us. But how far away are they? It wasn't until the 1600s that we got our first answers, one each from Robert Hooke, Christian Huygens, and Isaac Newton. Unsurprisingly, those early answers didn't agree with one another. But who came closest to getting it correct? Robert Hooke, a true pioneer of his time, embarked on a journey to unlock the secrets of the stars using the simplest, most straightforward, and direct way to measure the distances to them: the notion of stellar parallax. This idea mirrors a childhood game we all played. Close one eye, hold your thumb up at arm's length, switch eyes, and watch your thumb shift relative to objects farther away in the background. Whenever you have two different vantage points, objects that are close by will appear to shift relative to the objects that are farther away. This phenomenon, known as parallax, could theoretically be used to measure the distances to the closest among the stars, assuming they're close enough to appear to shift, given the limitations of our bodies and our equipment. In ancient times, people assumed the universe was geocentric, and so they attempted to observe parallax by looking at the same stars at dawn and at dusk, seeing if a baseline distance of Earth's diameter between the two observing points would lead to an observable shift in any stars. They did not. But in the 1600s, after the work of Copernicus, Galileo, and Kepler, scientist Robert Hooke thought the method might now bear fruit. In the late 1660s, Hooke went for it. He knew that atmospheric refraction, or the bending of light rays due to Earth's atmosphere, might be a problem. So to minimize that effect, he built what's known as a zenith telescope, a telescope that looked straight up overhead, minimizing the amount of Earth's atmosphere that light would need to travel through. Measuring the position of Gamma Draconis, the zenith star as visible from London, England, Hooke took multiple observations of the star over the course of the year, looking for any apparent shift in its position from true zenith to the best precision his instruments could muster. He recorded 4 measurements beginning in 1669 and noticed a variation that he claimed was observable with the precision of his instruments: 25 arc seconds, or about 0.007 degrees. He published his results in an attempt to prove the motions of Earth by observations in 1674, wherein he wrote, "'Tis manifest then by the observations, that there is a sensible parallax of Earth's orb to the fixed star in the head of Draco, and consequently a confirmation of the Copernican system against the Ptolemaic and Tychonic. The inferred distance to Gamma Draconis, according to Hooke, works out to about 0.26 light-years, or 16,500 times the Earth-Sun distance. Way back in 1668, a contemporary and friend of Isaac Newton, James Gregory, wrote a treatise entitled Geometriae Pars Universalis. Gregory came up with an ingenious method that, quite arguably, was superior to Huygens' method for measuring the relative brightness of the Sun to the stars to use a planet as an intermediary. If you can find a planet in our solar system whose brightness matches the brightness of a star precisely, and you observe that planet at that particular instant, then all you have to do is calculate a few key factors. First, determine how far the light had to travel and spread out from the Sun before hitting the planet. Next, know how much of the sunlight that strikes the planet gets reflected. Then, understand the diameter, essentially the physical size, of the planet he was observing. Finally, Calculate how the reflected light from the planet spreads out before it reaches your eyes. Gregory did a preliminary calculation himself, but warned that it would be untrustworthy until better estimates of solar system distances were known. Although Gregory, perhaps more famous historically for designing the Gregorian telescope, would die young at the age of 36 in 1674, his work did not end there. Newton possessed a copy of Gregory's book and was quite familiar with it. He worked out a more precise version of Gregory's calculations, perhaps as early as 1685 by some estimations. It was only after Newton's death in 1727, however, that his final manuscript was collected and published, seeing the light of day in 1728 under the title of The System of the World, De Mundi Systemate, even though it was originally intended to be the third volume of his much more famous Principia Mathematica. The advantages to using Gregory's methods were clear. You could observe Sirius and whatever planet you chose for comparison simultaneously, rather than having to rely on your memory from hours earlier to compare brightnesses. You could observe them under similar observing conditions, and in the aftermath of Newton's laws, and with Newton's reflecting telescope, it would be possible to both know the distance to the planets, and also their physical size at that distance. Although Gregory performed his initial estimates using Jupiter as a calibration point, Newton instantly recognized that Saturn, being the most distant known planet from the Sun at the time, would provide a better baseline. Although Jupiter always appears brighter than Sirius, and Saturn always appears fainter than Sirius. Based on observations by John Flamsteed in 1672, Newton knew that Saturn was about 9 to 10 times farther away from the Sun than Earth, and was also about 10 times larger in diameter than Earth is. What Newton didn't know, however, was how reflective Saturn was, what its albedo was. He guessed it reflected 50% of the light that struck it. And he also didn't know, just like Huygens, how intrinsically bright Sirius was. He assumed it was identical to the Sun. His answer was larger than that of either Huygens or Hooke, about 300,000 times the Earth-Sun distance, or in modern terms, about 4.7 light-years. The early pioneers laid the groundwork, but it was only in the 20th century that humanity began to truly understand the vast distances separating us from the stars. Advances in technology and an improved understanding of stellar properties enabled astronomers to refine their measurements with unprecedented accuracy. One of the most significant breakthroughs came with the advent of the Hubble Space Telescope. Launched in 1990, Hubble has revolutionized our view of the universe. By observing celestial objects without the distortion caused by Earth's atmosphere, Hubble provided data that led to the discovery of the accelerating expansion of the universe. This crucial finding earned the 2011 Nobel Prize in Physics and has profound implications for our understanding of dark energy. But Hubble is not alone. The Gaia mission, launched by the European Space Agency in 2013, has mapped over 1 billion stars in our galaxy with incredible precision. Gaia's data allows astronomers to measure stellar distances with unprecedented accuracy, providing insights into the structure and evolution of the Milky Way. And the discoveries keep coming. The James Webb Space Telescope, set to succeed Hubble, promises to peer even deeper into the cosmos, unveiling the secrets of the early universe and potentially identifying habitable exoplanets. As we stand on the shoulders of giants like Huygens, Newton, and Hooke, we continue their legacy of exploration and discovery. The journey started centuries ago, and it shows no sign of stopping. The stars beckon, and humanity answers, ever reaching for the unknown.